Picture a robot arm doing a task on its own. A policy is driving it, sending an action chunk for every observation from a server in the US. Then it slips. One of us has been watching the whole time from a laptop in Vietnam, and the moment the policy gets into trouble, we take the controls, correct the motion, and hand back one thing settled. Everything we do is recorded and aligned into clean training data as it happens. This is what we call human-in-the-loop data collection. It saves time and gives our dataset broader coverage of failure modes. In this video, we'll walk through how we built this with LiveKit Portal end-to-end. We'll collect data by teleoperating a real arm, train a policy on it, then hand control back and forth between the policy and a human while every correction lands in the dataset. Before we go into the tutorial, let's walk through our setup. We have a B601 rebot arm with 6+1 degree of freedom mounted on a table. A camera is on the gripper and another is on a platform on the side. The robot is controlled by this mini computer, which is separated from the teleoperator computer. We'll train the robot to pick up this microcontroller and put it into the container next to it. To connect our two computers, we'll use LiveKit Portal. It is a thin layer we built over LiveKit real-time infrastructure for operating robots over any network. It gives us three things against one robot from anywhere in the world: teleoperation, inference, and recording. Doing this over the internet is generally hard, and we don't want you to do it from scratch. The camera feed and the joint readings travel separately and arrive at slightly different times. So something has to stitch them back into one coherent snapshot before a policy can use it. Then we have to arbitrate between different policies and operators. Portal handles both for us. In Portal, there are two roles. A robot publishes what it observes and runs whatever action it's told to. An operator receives those observations and sends actions. A human teleoperator is an operator. A policy is also an operator. To Portal, they're the same thing, and that's the whole trick that makes our handoff works. In Portal, all roles share one configuration file, portal.yaml. This is our contract. It declares what the robot sends and what the operators receive, so the schema can't drift between processes. State and action are both 7 absolute joint positions, 6 arm joints, plus the gripper. We run observations at 30 FPS with 2 cameras, the arm camera and the overhead camera. On the robot side, we run a small Python script. The script reads the Portal configuration file and sets up a LiveKit room for us. This is abstracted behind a class called robot. We can connect the robot to this room using a LiveKit token, and our transport is ready to be used. To control our robot, we run a while loop. Each tick does 4 things. Read an observation from the follower arm. Send the state at each camera frame on one shared timestamp so the operator can fuse them. Then apply the latest action it's received. The actions are handled using Portal's callbacks. As we receive one, we update a global latest action to be applied every tick. The operator side is where our teleop, recording, and viewer are. The connection is handled the same way as the robot. In the while loop for the operator, we drive the leader arm and mirror everything into rerun so we can see what's happening. There's more plumbing on this that is not in Portal's scope. For example, how you record your data and how you align your action to your observation. In this tutorial, one dataset row is recorded per action. We keep a short ring buffer of recent observations. When an action comes in, we look back for the latest observation that came before it and pair them. The teleoperator action is naively paired, while the policy's action has an exact timestamp per observation. Now, let's collect some data together. For this tutorial, we'll run our own LiveKit SFU on our local network. The data transport latency in local networks is roughly 20 milliseconds, while on the internet it varies between 30 milliseconds and 300 milliseconds depending on the distance between you and your robot. On the robot host, we start the robot script. It waits for the cameras and the CAN bus, then sprint connected. We're in. On the teleoperator's machine, we start the teleoperator script. Rerun will spawn and we can see the robot states, cameras, along with the session's metrics such as end-to-end latency and number of stale frames. Now we take control of the robot arm and record some data. For this video, I recorded 50 episodes. I then published this dataset to Hugging Face, and you can see a visualization here. I then trained an action chunking transformer using this dataset. I used SkyPilot to orchestrate our training job on an H100 instance on Nebius. The entire script can be found on the tutorials repository. As we have our policy, we can now drop it in for inference. As you can see, the robot script and the teleoperator script are still running. Now we start the policy as the third operator. A policy, after all, is just another operator. It loads the same portal.yaml, subscribes to observations, and sends one action per tick or an action chunk. On the teleoperator side, we can easily change control between us and the policy. The policy is driving the arm, and we can start our data recording now. If the policy is getting in trouble, we can take control back, correct the motion, and hand it right back. No restart, no stopping the episode. Every one of those corrections we just made is now a labeled row in our dataset. Slight note here. Normally for human in the loop, to ensure smooth switching between human and policy, we often teleoperate using a VR headset or with a drivable teleoperator arm. Unfortunately, I have a teleoperator arm with only encoders, so we can't do that today. So that's the full loop we built with LiveKit Portal. One shared wire contract, a robot that publishes synced observations, operators that can be a human or a policy, and a recorder that captures whoever's driving. Cleanly aligned, correctly labeled. The whole project is open source, and we've written a step-by-step tutorial in the repo that builds this rig from the contract up. Links are in the description. Thank you for watching. We hope you go build something with it.